Did you know there are only about 5 ships on the entire planet, each costing roughly $400 million, that control the flow of electricity from the world's largest offshore wind farms? Without one of these specialized vessels, a finished wind farm standing in the open sea is just a row of expensive turbines spinning for nobody. The power has nowhere to go. To connect those turbines to the cities that need them, you need a single piece of hardware that almost no one outside the industry has ever heard of, and a material science breakthrough hiding inside a black cable on the seafloor. An offshore wind farm can sit 50, 80, even 120 miles from shore. Each turbine generates electricity, but that power has to be gathered, stepped up to enormous voltages, and pushed across the seabed to a substation on land. The link that does this is the export cable, a single continuous conductor that can run for over 100 miles without a break. That cable is the bottleneck of the entire renewable economy, and it is far stranger than it looks. Here is the core problem. To move huge amounts of power efficiently over a long distance, you have to use very high voltage. But high voltage inside a cable buried under salt water is a destructive force. The electric field wants to tear through anything around the conductor, and if the insulation fails, the cable shorts out, and repairing a fault under 60 meters of ocean can cost tens of millions of dollars and months of lost generation. So the insulation has to be nearly perfect, mile after mile after mile. The answer is a material called cross-linked polyethylene, often shortened to XLPE. Ordinary polyethylene is just plastic, the same family of stuff as a shopping bag. On its own, it would soften and deform when the cable heats up under load. But during manufacturing, chemists trigger a reaction that ties the long polymer chains together into a three-dimensional net. Imagine a plate of loose spaghetti suddenly fusing into a single molecular web that cannot slide apart. That cross-linking is what lets the plastic hold its shape and resist the electric field at temperatures that would melt the raw material. The hard part is purity. A single speck of contamination, the size of a grain of dust, inside that insulation becomes a weak point where the electric field concentrates, and over years it can grow into a branching crack the engineers call a water tree. So the polyethylene has to be manufactured in conditions cleaner than a hospital, extruded around the copper core in one continuous flawless layer, and cooled so slowly and evenly that no bubble or void ever forms. A flaw you could never see with the naked eye is enough to doom a $100 million cable. That manufacturing demand is why so few companies on Earth can make a high-voltage subsea export cable at all. The factories require vertical extrusion towers, some over 170 meters tall, where the cable is built hanging straight down so gravity does not deform the soft insulation before it sets. Only a handful of firms, concentrated mostly in Europe and East Asia, own this kind of plant. They are booked years in advance, and the queue for capacity has become one of the quiet choke points of the global energy transition. Now back to the ships. Making the cable is only half the battle. You then have to carry it out to sea and lay it on the bottom without kinking it, snapping it, or letting it twist as it spools off the deck. A continuous cable can weigh well over 10,000 tons. You cannot splice it together in the water, so the whole length must travel on the vessel in one enormous coil, wound onto a rotating turntable that can be wider than a soccer field. The most famous of these vessels is the Leonardo da Vinci, operated by the Italian cable giant Prysmian. It can carry around 17,000 tons of cable in a single load. As it moves forward at a crawl, sometimes only a few hundred meters an hour, a remotely operated plow or jetting tool digs a trench beneath it, and the cable settles into the seabed behind. Dynamic positioning thrusters hold the ship to within a meter of its track, fighting wind and current the entire way, because a single hard tug can ruin the cable it took 2 years to build. This is why there are only a few such ships in the world. A vessel like this costs in the neighborhood of $400 million and takes years to design and build. The combination of a giant rotating carousel, the most advanced positioning systems afloat, and the burial machinery makes them some of the most specialized industrial machines ever launched. They are not container ships you can order off a shelf. Each one is a bespoke factory that happens to float. Put those two scarcities together and you get a genuine geopolitical chokepoint. A country can have the wind, the money, the turbines, and the political will, and still wait years to connect a wind farm simply because both the cable factory and the ship that lays it are fully booked. When demand surges, as it is across the North Sea and now off the coasts of the United States and Asia, the limiting factor is not power generation. It is the narrow industrial base, capable of insulating and installing the cable. That scarcity hands enormous leverage to the few companies that control it. The major cable makers and their installation fleets can effectively decide whose wind farm gets connected first and whose waits. Governments now sign contracts to reserve factory slots and ship time half a decade ahead, much the way airlines reserve aircraft before they are built. Whoever controls the cable and the vessel quietly controls the pace at which an entire nation can decarbonize its grid. There are efforts to break the bottleneck. New cable factories are being built in the United States and elsewhere, and new vessels are on order, though each takes years to deliver. Engineers are also pushing the material itself, developing cleaner XLPE and even higher voltage formulations so a single cable can carry more power and reduce how many crossings the scarce ships have to make. But you cannot conjure a 170-meter extrusion tower or a $400 million ship overnight. And that lag time is built into the energy transition, whether we like it or not. So the next time you see a row of offshore turbines turning serenely on the horizon, remember what it actually took to plug them in. Somewhere underwater runs a cable wrapped in a near-flawless web of cross-linked plastic, laid down meter by one of only a few ships on Earth capable of doing the job. The wind is free and the turbines are visible, but the real machinery of the transition is the invisible cable and the scarce vessel that buries it. Control those, and you control where the electricity flows.
If you found this deep dive valuable, hit the like button, drop a comment below on what tech mystery we should decode next, and subscribe to never miss an episode.